Well, good morning, good evening, good afternoon, everyone. I understand right now there are 45 participants in this call, and I am very honored to have been invited to be one of the people. So I thank you very much for that honor. And basically, a little bit of history here. Today, I'm going to be talking about my recent book, Model Thinking for Everyday Life. That's what my presentation is about, and it goes back to the okay. So screen sharing. Oh, there we go. Beautiful. So when I say change slides, you can change slides. Is that the way, or do I do this myself?
We will change the slides, okay?
You can change the slides.
Yes.
Okay, okay. So a little bit of history here. In 1919, the COVID lockdown started, and we knew it would be a lockdown for some period of time, at least a year. It turned out to be about 2 years, at least in the United States. And so I said to my wife, Liz Murray, who unfortunately has since passed away, I said, Liz, my nickname is Dr. Q, Queue, for waiting lines. I said, since we're going to have a lockdown for a while and I don't have anything else to do, maybe I should write a book on queuing. And I'll never forget the conversation. She said, Dick, don't do that. You've been there, done that. You've written everything you want to do about queuing. Think very hard for 2 or 3 days what you'd really like to do next. And that was just a wonderful conversation for me from my lovely wife, who I miss every day. And I thought about it for 2 or 3 days, and I said, the thing I really want to do is reach out to the general population and have them understand what model thinking is. And here I use the word model in two senses. Model meaning exemplary thinking, thinking to be emulated, and model meaning conceptual model and sometimes mathematical model. So that's the background. And at that point, I started planning and started writing the book, and it was a 2 year effort. And if the COVID-19 thing hadn't occurred, this book wouldn't exist. So that's kind of interesting. So let's go to the next slide. Okay, that's the Hong Kong conference. Hi, Hong Kong conference. And so this is the book, Model Thinking for Everyday Life. And next slide, please. And this is published by Informs. Informs is the world's largest operations research and management science professional society. And I have been honored to be president of Informs. Before that, I was president of ORSA, the Operations Research Society of America. And this is the first book they've ever published. So it was a big honor for me that they really wanted to publish it. Next slide, please. So I'm talking from Lexington, Massachusetts, and that's the Minuteman statue in Lexington Green, where the American Revolution started. And that's less than 1 mile. It's about 1 kilometer from where I'm speaking right now. So I'm from Lexington, Massachusetts, and that's where I'm speaking at the moment, from my kitchen. Next slide, please. So what are some other people saying about the book? Because before it was published, I sent out the draft of the book to some other people. Next slide. So you may have heard of Steven Pinker, famous professor at Harvard, filled with surprising insights about the hazards, ordeals, and pleasures of everyday life, revelations that seem perfectly intuitive after Larson has explained them. Uh, Next slide, please. And there's Mark Daskin. Some of you probably know him, uh, University of Michigan. And he thinks it should be required a book in various university courses. Next slide, please. Michael Horn, very famous guy. Learning requires effort, but rare is the book that weaves active learning into the text. Richard Larson's new book does just that to help each of us become someone who learns new things every day. Next slide, please. Sanjay Sarma. Again, all these people I'm quoting are authors of well-known books. Reasoning and abstraction are becoming very important in society today and also in short supply in curricula. Larson's book is really a fresh and innovative journey that subtly awakens that faculty, both playfully and effectively. Next slide, please. So I'm an operations researcher. I call operations research the world's most important and visible profession. Because if you walk down the street and somebody says, well, what do you do? And I say, oh, well, I'm an operations researcher. They stare at you with blank eyes. They have no idea what that is. And so, but operations research is, just turn it around, research on operations, operations of all types. They can be small, like queuing at a traffic light intersection, or large, like running a major international airline, or things all in between. So, and my entire career has focused on both research and practice. So I think it's applied physics to the world in which we live. So I've always enjoyed physics when I was a student, but I didn't want to become a physicist because then you're in a silo. But operations research is the physics of what happens in our lives. And I've enjoyed that ever since I was introduced to it by my faculty advisor, Professor Al Drake. And so that's what I do. Next slide, please. So in the book, we talk about some interesting things. In most logistical systems, you can speed service by deliberately inserting delays. That sounds counterintuitive. We'll have a little bit more on that in a minute. Next slide, please. Here's another one. In choosing the locations for wind turbines, you're going to get electricity from the turbines turning when there's wind. The location with the highest average wind speed is not necessarily the one that will provide the most electrical energy. So the one with the highest average wind speed, and you know why? You know why that's true? Because the electricity from the turbines goes proportional to the cube of the wind velocity. So therefore, you might settle for a place that has a lower average wind velocity, but a good fraction of time where the wind velocity is really, really large. Next slide, please. Okay, so we're in the United States. I am today, and our national pastime is baseball. I know baseball is foreign to many other countries, where soccer or what you call football is a national pastime. But suppose we have two baseball players, Tom and Dick, and Tom may have the higher batting average in each of 2 seasons. But if you combine the data on the 2 seasons, Dick has the higher batting average. That sounds impossible, doesn't it? Well, just a hint here. There's a hidden variable here. The hidden variable is the number of at-bats of each player. But anyway, next slide, please. This one is really bizarre. Simply moving chronically ill patients from one group to the next can increase the life expectancies of each group. Think of this in a hospital. You have Ward A and Ward B. Ward A has the lesser sick patients. Ward B has the patients who are seriously ill. Okay? So if you take 10% from Ward A, the sickest ones in the less sick place, okay, and you move it to Ward B, the life expectancies in each group decrease with no medical intervention. I'll let you reflect on that and think about that for a second, but it's true. Next slide, please. In most service systems where customers have to wait for service, queuing, again, I'm Dr. Q, the duration of the wait is not the most important thing about customer satisfaction. The Disney properties in Florida and other places in the world where they have the Disney properties, they are the Machiavellian experts of the psychology of queuing. So they can design queues where you wait an hour in the queue, and when you get out of the queue and you join on this ride, you're a happy person. So the psychology of queuing is much more important than the actual duration of queuing. This goes back initially to some of the studies that were done in the 1950s when elevators became important in high-rise buildings because post World War II there was a building boom of high-rise buildings, and there were elevators. Of course, most elevators in those days had human operators. And so people started complaining about the delays for elevators. This was in the 1950s. And a student from Philadelphia heard about this and said, I have to go to New York and see what's going on here. So he traveled from Philadelphia to New York. This was a graduate student, and looked at the elevators, and he looked at the people waiting. And indeed, they got mad. They were impatient because they might have to wait a minute or two or three for the elevator to show up at their floor. So the ingenious thing about this person, he said, maybe the problem is not the delay for the elevators. Maybe the problem is the complaints about the delays for the elevators. If we can reduce the complaints about the delays, even though the delays stay the same, we will have solved the problem. And now, how can I test that hypothesis? So he got some money for one building, experimental building, and he put floor-to-ceiling mirrors next to all the elevators in the entire building. Guess what? The complaints about delays for elevators dropped to near zero, but the delays themselves remain the same. So what happens? Well, guys who were wearing both the ties at the time could adjust their ties. Both men and women could make sure the hair was so straight and everything. And on occasion, men and women would coyly flirt with each other through the reflection of the mirror because it was less provocative than direct eye-to-eye contact. So the mirrors next to elevator solve the complaints about the delays for elevators. Next slide, please. So here's another thing. Some people equate a Google search and you get the answer to a problem as research. And in the book Model Thinking, we burst that bubble. We say the answer is not the answer, the process is the answer. And but so we develop critical thinking skills in the book, and we're less concerned about the exact answer, but the ability to put together a logical sequential argument that gets you to a solution. Next slide, please. So here's an instructive allegory. I'll try to be very quick here. In southern Italy, scientists, and here's this ball that's in the backyard of a monastery, and three scientists visit this backyard every day at 3 o'clock. And when the sun is out, they notice that the sphere is hot on the bottom and cool on the top. Hot on the bottom and cool on the top. And they visit this place in the monastery in their garden 3 or 4 days in a row when the sun is out, and each time the sphere is hotter on the bottom than the top. So the scientists delayed for a few days, and then the one scientist said, I have a theory about that, why that should be. And they got so excited, they showed up at 1 o'clock the next afternoon, and guess what they found? They found a monk going and rotating 180 degrees the sphere so that the hot part goes on the bottom and the cool part goes on the top. Uh, so you can't believe what you see unless you really understand the process. Next slide, please. So B.B. King, famous jazz blues singer. Any day I don't learn something is something new is a wasted day. And I think that's a good thing for each of us to think about. We don't have to learn something scholarly every day. Just learn about the name of a bird that's in your backyard or your garden you had never seen before. Something like this. Next slide, please. Okay, so pencil and paper. So we have pencil here and paper there. So I'm a pencil and paper guy. Next slide, please. So there's the paper. Next slide, please. So this book, Model Thinking for Everyday Life, is reflects maybe the fact that I'm not even a baby boomer. I'm so old that I'm a pre-boomer. I was born during World War II, so I'm probably the oldest person on this call. And I tend to be old-fashioned, and so I believe in active learning with pencil and paper, with the computers turned off, and with no heavy math. Complex technical issues can be addressed in simple, entertaining ways. And so we see the world around us in terms of models. And this is an interactive book. Interactive book. So every few pages, we ask the reader to use pencil and paper and reflect on what they've just read. Next slide, please. Okay, so here we have rain on a windshield of a car. Next slide, please. And a daughter and her mom. The mom's driving the car, and the daughter says, "Mom, how come it always rains faster when you drive faster?" And yeah, mom says, "Why do you say that?" "Well, because you have to make the windshield wiper go faster when you drive faster. So therefore, there are more raindrops hitting the windshield. So therefore, it seems to be raining faster when you drive faster." Next slide, please. Okay, so we scribble on some paper. Next slide. Trying to figure this out, and we scribble some more on paper. We drink a cup of coffee. Next slide. Get those sharpened pencils. Next slide. Thinking, thinking, thinking. Next slide. Thinking, thinking, thinking. Next slide. So in the book, mom has a conversation with her daughter that together they want to think through the question about raindrops on the windshield. And even if the mom knows the answer ahead of time, and chances are most moms would know the answer to the daughter's question, um, the answer she orchestrates is what we call a discovery learning discussion. So in the discovery learning, you have a conversation where the answer comes out as a result of that conversation. So even if mom knew the answer, she would orchestrate it so that she and the daughter could together in that conversation uh, discover the answer. Next slide, please. So this discovery learning is a key teaching and learning method, and we can thank Ben Franklin for that. And in the book's appendix, in the appendix to model thinking, we have a complete mathematical depiction of raindrops falling down and hitting the windshield of a car, the car going at X miles per hour, where X can be variable from 0 to 60 or something like this. But and so those who are interested in the math, including, what's the terminal velocity of a falling raindrop? Okay, it turns out to be 10 feet per second. 10 feet per second is what they travel at as a terminal velocity. Okay, so let's next slide, please. So Ben Franklin, tell me and I forget, and unfortunately today I feel awful that this is just what I'm doing. I'm telling you. Teach me and I remember. Maybe some of what I'm saying is teaching. Involve me and I learn. Involve me and I learn. So that's why we have the book as an active learning book. Every 3 or 4 pages, we ask the reader to get the pencil and paper going and answer some questions reflecting on the last 3 or 4 pages that they just read. Next slide, please. So the Model T Ford is a special case of a windshield. And if you think of the word, the English language word windshield, you can see from the Model T Ford why they had that phrase. Because rather than a horse and carriage, now you have a horseless carriage, the automobile, and the windshield is to shield the driver from the wind. And you can see the original windshield was a flat surface perpendicular to the ground. So now you know why windshields are called windshields. Next slide, please. So in the book also we have 2 chapters on flaws of averages, not laws of averages, flaws of averages. Uh, some of you might have heard the Garrison Keillor show that used to be a radio show in the United States. And that's the news from Lake Wobegon, where all the women are strong, all the men are good looking, and all the children are above average. And that's what Garrison Keillor would say at the end of the show every week when that show was on. Next slide, please. So you might say, by the way, I asked a question. Is it possible or impossible that all the children of Lake Wobegon can be above average? Okay, well, maybe if Lake Wobegon is in Wisconsin, or was it Wisconsin? I think it's a fictional place. It could be that all the students in that particular location are above average for the entire state. So it is possible for all the children of Lake Wobegon to be above average if the base is sufficiently large and it maybe includes the whole state. So flaws of averages. So another thing is what about the average inter-arrival time for buses? So the natural dynamics of buses. If you look at this photograph here, you see 2 or 3 buses all clumped together. So if you think about it, suppose the buses are dispatched from the origin part of a 6 mile route every 10 minutes. So if they're dispatched every 10 minutes and you show up at a random time, you kind of think intuitively that, okay, I'm going to show up maybe kind of in the halfway between the 2 buses. So my average wait should be 5 minutes. So that's a thinking you might have. Next slide, please. The problem is you have bus clumping. Buses in an urban environment tend to clump together. And you might ask, why do they do that? Well, maybe the first bus that gets going down the line all of a sudden gets to a stop where there are greater than average number of people boarding. Or maybe there's somebody in a wheelchair who needs assistance getting on in the middle door of the bus. So that bus then maybe is delayed an extra minute or 2 at that stop. The bus behind it arrives, and there's been less time for other passengers to accumulate there because the bus in front was delayed. So therefore, the bus behind bus number 1, bus number 2, spends less time at the stop than he ordinarily would because there are fewer passengers there, and so it gets ahead of schedule. So the bus number 2 gets ahead of schedule. Bus number 1 gets repeatedly behind schedule. So they clump together first in pairs and then in higher orders. So the physics of buses in municipalities, cities, is such that the clumping is a regular consequence. Next slide, please. So if you think about that, if you arrive conceptually, think about that. at a bus stop, you're basically parachuting onto the timeline. So the timeline, X is horizontal down there, and you're parachuting onto the timeline. And suppose you have, just as a thought process, you have buses that are a delay of 20 minutes, and then you have another one coming 2 minutes later. Then you have next bus that comes at 20 minutes, and the next one comes 2 minutes later. Okay? So next slide, please. So here, the mean time between bus arrivals is 11 minutes. So is our random arrival going to have a 5.5 minute delay? Next slide, please. No, if you go through this calculation, you see that the chances are an order of magnitude more that our randomly arriving passenger arrives in the 20-minute gap, experiences an average of 5 minute delays, 10-minute delays, and a very small chance, 1/11th basically, of arriving in the 2 minute gap, in which case the waiting time for the bus is 2 minutes. So we're unfortunately, as we parachute onto the time axis, we're more likely to arrive when there's a big duration between successive buses. Next slide, please. So that's the end of the bus saga. We have other examples of flaws of averages in the book, and I know I'm getting short on time, so I'm going to wrap up in 5 minutes or so. Shocker, half of all marriages end in divorce. This is a real statistic in the United States. Half of all marriages end in divorce. Next slide, please. Next slide. Thank you. Good news today, only 1 in 8 current marriages will end in divorce. Both statements are true, and they seem to contradict each other. Half of all marriages end in divorce. Only 1 in 8 current marriages end in divorce. I'll let you reflect on that, but it has to do with flows and levels. Flows and levels. Both statements are true. So the flaws of averages are really kind of interesting. Next slide, please. A final example, queuing. A.K. Erlang, Danish telephone engineer, invented the mathematics of queuing in Copenhagen, Denmark in 1919. There he is. Next slide, please. Next slide, please. And for those of you in the US who are old enough to have remembered Saturday Night Live, Lily Tomlin was Ernestine, the 1950s eccentric telephone operator. So she made telephone operators interesting to study. Next slide, please. But telephone operating correctly is very, very important. In the US now, throughout most of the US, we have a 911 system. So if you have a police, fire, or ambulance emergency, you just call the 3-digit number 911, and that gets you to your local emergency services, which will connect you to police, fire, and ambulance right from there. And there's a photograph of a 911 operation. Next slide, please. So queuing theory can predict what the delay will be for answering a call, depending on how many operators you have. And there's an example of 2 different graphs with 1 server or 10 servers. And on the horizontal axis is the fraction of time that they're busy. It's called rho, the utilization factor. Next slide, please. So I was called in when I was a graduate student. I was called in to help New York City with their 911 system, because as soon as they installed the 911 system, I think this was 1979 or something like that, you got letters to the editor of the New York Times and other newspapers Um Dear folks, I called the mayor's 911 system the other Saturday night and let it ring for 28 minutes. There was no answer. I hung up, thought it maybe I got the wrong number, and I called again. And after 25 minutes, police emergency, may I help you? So I called the police department and I volunteered as a Q theorist to come and help them figure out what was going on and how to solve that problem. And so I actually went and I lived in the police department headquarters and worked with two lieutenants for 1 month. So for 1 month, we worked together side by side, the lieutenants on personnel training and me on the statistics, the data, and the mathematical modeling of the queue. And what you see here is the data indicating, particularly, I think this was a Saturday night, where the call 24 hours of a Saturday, where the call rate, the hourly call rate changed by an order of magnitude between the least busy hour and the busiest hour. And yet the allocation of operators changed only by a factor of two. So they had this factor of two where from 3 o'clock in the morning to 7 o'clock in the morning, they reduced by a fact, but by half the number of operators. Other than that, they had the operators be flatly allocated over the course of the day, and you can see that that doesn't reflect the realities of the situation at all, and the delays get very, very, very huge on Friday night and Saturday night. So they called me in there, and so I was Dr. Q. I worked through all that. Um, and next slide, please. And basically, uh, we created 6 different shift schedules and overlapping shifts. And so the two lieutenants and I, they were the training, and we were the data and the math and the models worked out. And that was when I presented this to the police chief, who was a very stern person, and I got into, I had these charts, and he stopped me after a minute. He said, Mr. Larson, Dr. Larson, or Mr. Larson, your Easter Bunny charts are interesting, but they're not telling the truth. And he called them the Easter Bunny charts because I had pastel colors on them. And he looked over to the two lieutenants. Lieutenants, really, what's going on here? And the two lieutenants I worked with gulped. Sir, everything Mr. Larson is saying is true. And boy, the police chief really sat up straight and he said, okay, tell me more. I want to know all the facts, as difficult as they are. And every one of my suggestions was implemented within 1 week. Within 1 week of this presentation. It's the fastest implementation I've ever had in my life. In 1 week, the New York City Police Department had 6 different overlapping shifts and tours. And so that was that. Now, what this map here shows you is later on, I invented the hypercube queuing model. The hypercube queuing model, which models the spatial allocation of police cars and ambulances and their response patterns over the course of over the city. And I have them color coded by green being less busy, red being busiest, yellow being in between. And I developed the hypercube queuing model. I actually programmed it myself in the C language. It took two years to do this. And this was then subsequently used in New York City and other cities. I think it became the gold standard in spatial distributed queuing models for emergency services. Next slide. Next slide, please. So our focus is on informed critical thinking. We're swayed by facts, not emotions, not politics. And a critical thinker is aware of the pitfalls of human intuition. And we have shown many examples where sampling bias, devious means, and cues can be counterintuitive. And we really have to study this very carefully. Next slide. So we have one more topic. Do I have 3 more minutes? Do I have three? Okay. Hopefully we have 3 more minutes. Going way back to the 1972, the Fram oil filter commercial. And we have this guy with the Fram oil filter. He says, "You pay me now or pay me later." And no, and now those days, pay me $8 to put in a new oil filter now, or pay me $800 for a new engine 3 months from now if you didn't do that. So that's deferred maintenance. That's the last example, and it's the last focus in the last chapter of the book. Next slide, please. So examples of deferred maintenance: your car, your house, fire alarms in the fire extinguisher, yourself. You may have deferred maintenance on your own body, your friendships, and my retirement from MIT was deferred maintenance. I should have retired at age 65, but I've retired in my 70s. Next slide, please. So I actually I wrote an article on retirement, and because I've actually decided to study it. When I was in my early 70s, I said to myself, why am I not retired yet? Because when I started at MIT as an assistant professor, mandatory retirement was at age 65. And then the federal rules changed to the mandatory retirement was at 75. And then the Supreme Court said you can't have any particular age for mandatory retirement because it's unconstitutional. So technically, you can be 110 years old and still working. So I wrote an article on that, published in Science Magazine, called "What Are You Waiting For?" Next slide, please. And basically, that's all. We're all done. Thank you very much for your time. I appreciate it. There's still 48 participants, so thank you for listening. And if we have